Start recording. Alright, now I've just cut all that out. Ta-da. Admit. Come on. What's up? I might have an answer for
So
you.
since are we gonna have lab on Friday, or
There will be a lab on Friday, yes.
will you
Um,
be, or is it gonna be Merrick?
um, I don't know. Um, if depending upon how I feel, it'll be myself. If I'm not feeling well, I don't know what will happen there. Um, we'll have to make arrangements when the time comes. It may be Merrick, it may be someone else. I don't know. What I suspect will happen is that we might be able to get Tyler to supervise physics 1, and Merrick will do physics 2. The problem is that on Friday, Merrick has a lab at the same time. We intend to not move labs any more than is necessary, but stuff happens. So we'll find out later. That's we'll all find out later kind of problem. All right. So okay. Okay. Alrighty. So today we start on chapter 22, which is E&M induction. Come on. There we are. Alright, so induction. So the fancy way to do this, there's a fancy way to do this, which we will not do ourselves, is this guy here. This is called Faraday's law of induction, as in Michael Faraday. He is the guy that we named capacitors, the unit of capacitance, farad for. So we got all this mumble jumble here. What this here it says is some of how about let's go about this? Let's say that if there's no magnetic field changing on the right side, then this would simplify it down to the sum of voltages over a loop is equal to 0 volts, and that's Kirchhoff's loop law, right? Remember that guy. But what's actually going on over here is that this is a little bit of electric field for a little bit of distance. And so this is basically summing up what a capacitor looks like. There's ways to get a resistor in here and stuff like that. This guy here on the right, we have what we have here in more simple terms is a changing something over time. And so we got a B vector with a dot A. And so we actually come back to the concept of flux once again. This time, instead of the electric flux, is now the magnetic flux. And this is equal to our electromotive force. So if we have, so remember how we have a electromotive force kind of thing? That's measured in volts. Well, it's one of the elements of volts here. So we have So this flux guy, he's back. Dang it. So that flux character is back. Instead of having the electric flux where it is EA sine of the angle between E and A, just as it was last time. This time it'll be with the magnetic field. So it's basically the same idea, just a change in the units, the change in the identity of the field. Dang it. Nope. I gotta go through the sound and edit out my cough skin. That's a pain in the butt last time. Anyways. However, because this is so useful to us, there is a unit for this guy. So we have a Tesla meter squared. So this is our unit for magnetic flux. And so the unit for magnetic flux is a Weber. Like so. I don't know who this character is at all. So, I have made a note to myself to talk about conceptual example number 8. Ah, yes. So, what is this going on about here? What is this statement talking about here? Dang it. Alright. So, if I were to have a loop of wire, with some resistance in it, let's back that up just a little bit, try again. A loop of wire with a resistor in it, like so. And I approach this loop of wire with a magnetic field. So I'll go here, north goes here, it comes this way, and like so. And it approaches this loop of wire with a velocity. What's going to happen here is that the increasing magnetic field inside this loop of wire is going to produce a magnetic field which opposes the magnetic field that's approaching it. So, what it's trying to do, and more often than not unsuccessfully, is that it's trying to oppose a change in magnetic field. So, EMF, let me back that up just a little bit. Induced EMF creates a current and magnetic field that opposes. This is the big idea here with my inductance, with my induced, with my electromagnetic induction. So that induced EMF creates a current, and the current produces a magnetic field that opposes the change in magnetic field. Come on. Try a little more. Magnetic field. Dang it. Edmund. So, if I approach this loop of wire with this magnetic field, it'll oppose that with its own magnetic field. And so in order to oppose it, the magnetic field has to be to the left, and so it's going to produce a counterclockwise current to oppose the approaching magnetic field, magnet here. Make sense? Questions about that? This bit here is the bit I care about the most.
I had to adjust my mic. So, if you don't care for me to try to repeat it so that I can understand.
Yeah.
Basically, the the magnet approaching is it, like the text says, makes an electromagnetic force, and I'm just confused. Like, what does it mean that it opposes the change in magnetic field?
So here, because my magnet is approaching with this magnetic field to the right, and that's increasing, right? So it's increasing it with a magnetic field to the right. And so in order to oppose that, it must produce an induced magnetic field to the left. If I were to withdraw this magnet with this magnetic field pointing to the right, that means this magnetic field would be decreasing. And so it would reinforce the loss of magnetic field with a magnetic field pointing to the right to reinforce the loss of magnetic field if it were to retreat to the left.
So as a magnet gets closer, wait, so the magnetic field of the magnet that's approaching is pointing to the right,
Correct.
and the magnetic field of that of the circuit is pointing to the left to begin with.
The yeah. The induced current will create a magnetic field in response to the changing magnetic field.
But it didn't have a magnetic field to begin with.
Correct. Because initially the magnet was sitting somewhere. Who knows where it was sitting? And so that means that the current there's no changing magnetic field inside that loop. So it's just going to sit there, and then you approach it, and it's going to oppose that change.
Okay, so the B, I was confused by the B pointing to the right because I assumed that was maybe the innate magnetic field of it, but I didn't understand the I is induced.
So that's a B there. And then this B here. This one is induced, and it came from this current here that was induced. Should I draw it a little bigger? I'm running out of space.
There are functions to zoom in.
Yeah. Well, there's running into this. I'm at 100%, and so it's not going to get any prettier. Got a north here, a south here. Magnetic field comes in like this, goes into the south end like so, and approaches with some velocity. Control Z. Some V goes there. So got a loop with some current in it, with a resistor. And so it's going to approach with some velocity. And so so that means that the and so we got B here. B increases to right. To right, like so. So then I will have a induced EMF going this way. So we got we'll have an EMF that makes a I induced. If I spell right, induced, and that I is going to go in a direction such that it will produce a magnetic field B induced that will oppose B induced opposes this statement. So in order for B induced to oppose the incoming B, that must mean that the current induced is going counterclockwise through the resistor, and EMF will all make it all work out. If I were to withdraw, where is my, grab that guy there. If I were to withdraw this magnet it will now go to this way, which means that my B induced will need to reinforce this. So now my B induced is now decreased. My magnetic field is now decreasing to the right, which means that my induced magnetic field needs to reinforce it to oppose this decrease in B, which means that my induced current will need to go clockwise. It makes sense now?
Yeah, it makes more sense than it did before. Sorry.
Very good.
Hard to mess
It's
with
alright.
mic stuff.
It's alright. 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 It probably doesn't help that I'm all rumbly and whatnot. Like I've been yelling, but more like coughing, hacking up a lung. Alright. So. Okay. Alright. So. Right. So the thing is that the thing I care about in this class is that the EMF is equal to negative change in magnetic flux over change in time. This is, depending on who you ask and when you ask them, this is Faraday's law. Formally, this is Faraday's law. But from another perspective, it's also Lenz's law. If I spell his name right. I'm probably not spelling it. Yeah, I didn't spell right. Because Germans and Austrians are weird. I think they might actually be Swiss. I don't know. Oh, Russian. Okay. The Russians are weird. Okay. They're basically the same. I think there might be. The book has written it slightly different than what I would do here. I don't blame him for it. To be more, to encompass more situations, such as loops of wire, we need an in here. And so this will be loops of wire. Okay. So now, if I take let's see here. There's a particular idea that the book has derived in one particular way, and then it derived it another way, and I like the second way better. If I make some nice straight, well, I got ways. I know how to make straight lines here. Okay. Control right? Nope. Shift? Nope. First, I gotta tell it that. Now I have to make shift. All right. And control. Let's control. Make it a yes. Lock it down. Whatever. I have a feeling I did that in the wrong order. And all right, now I got some nice straight lines here. All right, so I got some wires. This guy's got a low resistance in him. Put my R on him. And so I got some wires. This guy is falling down with some velocity v. And we're in a magnetic field. Let's go like so. Let's put our magnetic field into the paper or board or screen, whatever you want to call it. Like so. Of course, we need to keep going. Alright. So. Alrighty. Let's see here. We have a B field. Into there. Okay. So now I can figure out my EMF off this guy. EMF is equal to minus change in magnetic flux over change in time. Oh. Well, I got magnetic flux here. Magnetic flux is like we've had before, where it's B times A. So that's minus change in B and A over change in time. But B is constant. And A, well, we'll make this guy here, we'll make him L wide. And so A, the area of rectangle is width, which is L, and our height. So that will be V T for the height and L for the A. Right? So so then we take the L out and the B out, so this ends up with minus B L, and then we have the change in area. The L came out, so left with VT over change in time. Oh, what's this guy? So I have this change in VT over change in time. Well, V is constant, but this T is changing 1 for 1 over time. So that means that my electromotive force here is minus BLV. The book prefers that in the order of minus VBL. Like so. So this is what is known as motional electromotive force, because a thing is moving. And so what the book wanted to talk about, how they initially derived it, was the fact that we have a rod of metal moving in the magnetic field with free electrons. Okay. So that means that I have electrons to which the magnetic force is acting on. And so we end up with QV cross B, with Q being negative. So that means that, let's see here. V is down and B is into the page. So that means that if it was positive, it'd be to the right. So I end up with all my electrons over here, and I have a deficit of electrons over here. So this end turns negative, and this end turns positive. And so I end up with a current going that way. Come on. And you'd end up with the you'd end up with the electrons over here and the missing electrons over here, regardless of if you completed a circuit or not. And it's like, well, that's a very pretty demonstration of what's going on, but I don't know if I care that much about it. But this is a case where the requirement that the magnetic field does no work was getting to me in this particular case. And it turns out that I wasn't paying attention to the whole situation about what's going on here. What happens is that I end up with an electric field E here, like so. And it turns out it's the electric field that's doing the work and not the magnetic field. So it's like, okay, I'm trying to figure out how the magnetic field was doing work here, and that's how it's doing it. By not doing it and pushing it off to the electric field. Did I do this right? Current should flow with the E field. Why have I said the current will go that way? My field is increasing, so it should do that. I'm not sure. That's weird. I is definitely going this way. But the E field always goes from positive to negative, so I'm not sure what I've done here. That's a little funny. I've done something a little funny. Because the E field should go with the I. Anyways, that's a little weird. Anyhow. So, questions about this other than that E field?
So the electromotive force with the symbol you're using for it, I think it's epsilon.
Curly E. It's supposed to be the curly E.
That's the only two of those we have is like that as the permeability of free space, or permittivity of free space, and that is electromotive force, right? There's no other value using that symbol, or are there?
Nope, that's it. It's supposed to be drawing here is the curly E, as opposed to an epsilon, which is supposed to be more like that instead of needs more of a loop here. So if you go look at your book, they are definitely not the same. My ability to distinguish the curly E and the epsilon on board is garbage.
Gotcha.
All right. So, stop moving on me. So there is an interesting problem I'd like to explore here. Do I care about any of this hanging around? I think I need to get rid of most of this. So, I want to hold on to that. And I want to get rid of these guys here. And we'll hold on to that one. Delete that. And that. Move that up to here. And then we'll get rid of all these guys over here. We don't need them. Keep this. Push it up to here. And delete this guy. And we're going to keep this guy here. Alright. So, a little more. Let's get a little more to the left on them. Doink, doink. Alright. There we go. Alright. Oop. Nope. Try again. There we go. Okay, so conceptual problem number 3 Right? Is that the one? Yeah, that one. Alright. I've got a variation on conceptual example number 3. I really did like this one. Alright. From Texas A&M's battery of problems. So this is extension to, or variation on, if I can spell right, conceptual example 3. Alright. So given this situation here, let me get a little more of it off this that we don't need. We don't need that, or that, and we don't need, nope, not that one. Dang it. This isn't gonna work. Get rid of that. Without getting rid of the line. Alright, close enough. Alright, so I would like to know, given that my magnetic field is, we'll make it 0.75 Tesla. My resistor is, we'll make it 100 ohms. And I think I'm going to need the mass of my rod here. So mass of the rod. That's falling down. I think we'll make that, make 0.1 kilos. I think that's all I need. And what I want to know is the velocity of my rod as it falls down. Okay. Okay. So. Okay. So, alright, so what forces do I have acting on my rod here? What are my forces? I have 2. What are they? I'll take care of the easy one. I got gravity pulling it down. And what's pulling it up?
In this case, if it's like a metal rod, maybe
yeah,
it's getting interacted with magnetically.
Yeah, it would. So I'll have a magnetic force acting on it. Not just because it's metal, but because the EMF will have induced a current flowing through it, right? So that induced current is going to have a force acting on it. Okay, so I have mg pulling down minus my magnetic field. My magnetic force is going to be I LB. And since my I is going to be going across this wire one way or the other, that must mean that my sine will be of 90 degrees and sine of 90 is 1, so I don't need that. So 0. Oh, I guess I do need the L. Well, 0 newtons. Looks like I do need the L of that, so let's make it. Let's make it half meter. Alright, so now I can figure out what my I here is from this guy here, right? So this is this EMF is equal to IR, like so. But we also know that this EMF is also equal to the emotional EMF. We don't need to go through that derivation again. I don't feel like doing that. We don't need that. So I'll just go ahead and write that down. Bugger. BBL. Okay. Aiden, your mic is hot.
Oh,
Alright. So that means that I can figure out what my current is. So my current is equal to VBL over R. Okay. So now I have my current right here. I guess we didn't need to know my length then. So I have mg minus, take my current, stick here. V B L. Oh no, we did. Yeah, we do. Never mind. Over R times L and B equals 0 newtons. Okay. So that means I can solve for B now. Oh, not B. I can solve for my velocity. So mg is equal to V B squared L squared on R. Solve for the solve for this guy. Multiply by R on B squared L squared. R on B squared L squared. So now I have that my velocity of this bar that's falling down is equal to R mg divided by B squared L squared. So my resistance is 100 ohms. My mass is 0.1 kilograms. My G is 9.8 meters per second squared. Divide by 0.75 Tesla and a half meter quantity squared. Calculator, what is this value? 100 times 0.1 times 9.8 divided by 0.75. Oh, for fruit's sakes, one moment. Times a half and squared equals 697. 697 meters per second. Uh-oh. Okay. Alright. In about 14 odd minutes or so, I'm going to need to restart this call because, once again, I did it on the wrong account and now there's a time limit. Yes. What joy. So when time runs out, I guess that'll be a 5-minute break. Whatever state we're in. And I'll send out a new link because apparently stuff happens. Alright, let's see here. Let's double check our units, make sure things aren't being weird on me. I would like a new tab. Preferably not in this window. Give me a new tab. Thank you. I would like to, if we're going to check our units properly, like I said, I don't like memorizing these units. Let me sit over there. So, let's go look them up. Tesla unit, thank you. Alright, so that is a Newton second per Coulomb meter. So Tesla is a Newton second per Coulomb meter. And an ohm. Not you. Let's grab the right one. Oh. And we'll go grab the ohm. Make sure we get his units right. Yes. And the unit of ohm. Basic unit of ohm. What is that? Let us go with let's go with kilogram meter squared per second Coulomb squared. Oh boy. Let's just grab that. Grab that. Copy it. Paste it there. Give me the moon. Alright. And drop it. Thank you. And that back. And this is the ohm. Alright. Let's work out units. Make sure that I haven't screwed that up. So we have a kilogram meter squared per second Coulomb squared times the kilogram and a meter per second squared divided by a Newton second per Coulomb meter and another meter squared. Alright, so this guy cancels with that guy. This inverse Coulomb squared cancels with this inverse Coulomb squared. And then what? Oh, we need to be making a Newton squared out of stuff. So this second comes up to here and makes a squared here. And then this is a Newton. And that is a Newton. Newton there. Newton there. And we'll cancel with that Newton. Except for... Uh-oh. Oh, I did it wrong. Hold on. Alright, try again. Alright, so this Coulomb square still cancels with that Coulomb square. This... Dang it. This is a second square and doesn't add 1 to this. It adds 2 to this. So I'm going to actually put it here as another second squared. This here. That, oh, not quite. I'm going to scratch this guy and pull 1 meter out and leave him over here. Now that's a Newton. And this is a Newton. And we'll cancel with that Newton square. So this will all go away. Cancel that and that. And now I'm left with, aha, a meter per second. Check. Alright, units to check out. Very good. That's why I don't like my my E&M units. 1, there's a lot of ways to arrange them. 2, there's lots of units that stack into each other. And it makes it really hard to figure out what's what. So if you don't memorize them, I don't blame you, because I haven't. Anyways. And let's double check, make sure that that my magnetic field is indeed pulling up. Alright, so. Alright, so. My magnetic field is pointing into the board. So because my flux is increasing, my induced magnetic field will oppose it. And so to do that, my eye will go counterclockwise. So that's going across to the right. And so now I need to check that this guy here is pointing up. So that will be I cross B. I to the right, cross B into the board. Leaves with my thumb pointing up, so it does indeed go up. So everything checks out as it should. Ta-da. I really should have checked this direction beforehand, because, it'd be weird if we were, accelerating, and then we'd have a different problem. Okay, so, let's see here. Alright. You know what? That was an excellent place to take a break. So, I will send out another link to another Google Meet here by email shortly, and hopefully we'll be back together within 5 minutes. Oh boy. More than 5 minutes has elapsed. The recording has resumed. So I suppose it's time to get started again. It's so good to make these meetings with the right account instead of the wrong account. All right. So, how does an AC motor work? AC motor. All right. So we have a magnetic field. Admit. Umshot is once again using her private account instead of the school's account. All right. Anyways, so when I was using my private account, I had to let you all in. Because this is on my school account, only those not using the school account have to be let in. Alright. Anyways, so we have a B field, like so, and then we got a loop of wire floating in this loop in here. And I need a way to pull out of this loop a current into the rest of the world. So this guy is going to do over there. Oop, try again. This guy goes here. This guy goes here. This guy goes into a bushing. It goes like so. This guy goes over here to a bushing. They're called rotational couplers, something like that. And so then this goes over here, and this will go over here to some load, whatever is on the grid. And so this guy is going to rotate, like so. And because we have a rotating loop of wire in this magnetic field, we're going to be changing. So I have a loop of wire in a magnetic field. And it's A field, it's A, is going round and round. And so the magnetic flux goes as N A B sine omega T, like so. And so this guy is changing with time constantly. And so that means that there will be an introduced EMF as a function of time. And so, okay, here's this thing, very good. And so, and so because it's always changing, we're always going to the EMF in here. So that's how an AC motor works, right? So, what if on the other end of my AC motor, instead of just a simple resistive load, I had the exact opposite of this, where I have a loop of wire that is rotating in its own magnetic field. Right? But this time, what's going on here isn't that it's just, we're generating power in here. What's going on here is that this time it's rotating because of torque being equal to torque is equal to, I don't rightly recall this one, torque, there it is. Torque is equal to N-I, okay, well, that's not my problem. Not for another month or so. N-I-A-B sine of phi. So, between A and B. So this guy is going to be rotating because of this torque here, because of the current and the magnetic field and all that. So he's going to be rotating, right? So this is an AC motor. Oh, that's not right. That's me. Remove that and replace it with something more proper. It's not just an AC motor. It's an AC generator. And so this guy's rotating. So this guy's rotating because some mechanical torque is being imparted upon it. Whether that's the forces off a steam turbine or a water turbine in your hydroelectric dam, or the wind turbine in your wind generator, or your, I think those are the big ones. Most of them are steam turbines in gas, coal, nuclear, and geothermal. Will be using steam turbines to rotate this guy. And so this guy will rotate for a torque because of the current in him, because he's an AC motor. But what distinguishes an AC motor from an AC generator? The answer is nothing. So that means that this AC motor here will make its own back EMF off this thing going around circles, which means that the current that it draws will be less than what you would think otherwise. So you got a voltage that you're applying to this electric motor here, and then you're going to subtract off of it the back EMF from this guy here and divide by the resistance in the motor. So the current that you actually draw would be less than what you would have expected otherwise because of this particular effect. Because of Faraday's law here, or Lenz's law, we do not, the induced current in the loop here opposes changes to the magnetic flux as it goes rotating around, and that opposition to the change in magnetic flux produces an opposition to the current that we're trying to push through there, and so that's going to produce, and so that's going to be a back EMF pushing back on all this. I suspect that if you're to actually crank on AC motor like this, you might actually feel that resistance being pushed back on you. Yeah. Anyways, questions about back EMF? It's not a huge topic, but it's a thing. It's like, oh yeah, that's a thing. It's in the book. I might as well talk about it a little bit. Right. So, the book has been kind enough to derive some stuff. Where did the 2 come from? All right, yeah. All right. So this EMF produced by this electric AC generator here. The book didn't properly derive it, but it did. It waved its hands in the general direction of the derivation. This is NA B omega. I think they did cosine on theirs, didn't they? No, they didn't. They didn't specify. Or maybe? I don't know. I don't think particularly matters a whole lot. Cosine omega t. And so you can reduce this down just a bit if you want to. You can say this is some EMF magnitude. Cosine omega t. Where that omega is, once again, 2 pi frequencies. And F is generally, come on, no, for the beat, 50 hertz if you're not in the Americas, or 60 hertz in the Americas. That's terrible. Perhaps another day. Oh, and this. Oh, I dropped 2, didn't I? I needed that 2. Sorry. Dang it. I'll put 2 on the end. So, because of the fact that we get EMF off of the fact in one direction and also the other direction as it rotates around, there's a 2 that shows up apparently. Do I care about anything else in here? Not in particular. Alright. Questions about the AC motor? Do I have... Oh! I have selected for myself number 32. What is number 32? Oh, yes. That one. Alright. Number 32. I have a constant magnetic field into the page. Like so. And then I have a loop around it. And then I have this half loop here. Like so. And that half loop has a crank on it that will rotate like so. I bet you do have a radius, or is it one has been drawn? R goes here, and we have a resistor, R here. This here. Oh, for the Pete, really? Well, of course. If we're going to be like that, they're going to be keeping it simple. Alright, starting in this position here, on top, and then rotating. Starting from this position, indicating the drawing. Semicircular wire, piece of wire, rotates through half a revolution in the direction shown. towards us. So if I have my B field going like so, and my loop of wire, come on, let's make a loop, my loop here. And it's going to rotate over this way. And it's going to rotate down to this position here. Which end of the resistor is positive, the left end or the right end? Explain the reasoning. Aye. So, basically asking which way does I flow? Okay. So my B is going into the paper. And so I'm going to reduce the area. So that means my magnetic field is my flux is going to decrease. So B induced will oppose that. Will reinforce B. Okay, so that means that to enforce this B that's going into the page, I need to make a magnetic field like so. And so my right hand is showing that my current is going this way. It's going clockwise. So that means that if there's a positive end, it's going to be here, and my I and my minus end is over here. Because electrons are weird. Questions? Make sense? Hearing none. Is there any other here that I really care about? Lenz's law? I don't know if there is. Let's check out if there's any other Faraday's law. Oh, right. Did I pick one of these out? No, I picked out one for this page, didn't I? Yeah. Okay. All right. So. All right. I feel like I have talked enough about Lenz's law and Faraday's law enough. They are effectively the same, but slightly different. I think Lenz's law. Faraday's law. I think Faraday's law is the general case, and Lenz's law is what happens if you have a moving loop of wire. So if your loop of wire moves into the magnetic field, that's Lenz's law there. But it's like, what's the difference between magnetic field changing and according to the magnetic flux, what's the difference between a change in magnetic field and a change in the area of the loop? Well, as far as it's concerned, nothing's different. It just looks a little different. It's a question of mechanism and not a question of how. Anyhow. So, if we got inductance, we can. So we have an inductance with an EMF. That's a voltage there, isn't it? So that means that in our loop here, in a circuit, we can have a battery and a resistor and an inductor. So this is R, this is H, my inductor, and this is my V battery here. Okay. So I can have not really. Okay. All right. So if I wanted to, I could have a magnetic field here. I'm going to put an AC circuit on him, like so. And so he's going to make a magnetic field here. And right next to him, I'm going to put another coil. And I'm going to put a voltmeter on him. That probably implies a resistor of some kind. So we got an R here. H is not the right letter for that. My apologies. Let me get the. Let me remove that. L for some reason. Don't ask me why. It was English momentum last semester, after all. So I have a B field here that's going to be acting on this guy here. And so, so we're going to have some number of coils and a magnetic field, magnetic flux on him. And we're going to call this guy the secondary. Oh, come on, I need a little more space. Secondary. And this guy is going to be the primary. The primary drives the circuit here. And so there's a whole bunch of geometry nonsense hidden in this M here, but there's going to be some amount of current flowing through this guy here. So I primary. So remember from last week where we had that the B field was equal to, for a wire, was mu I over 2 pi r, right? So this is the B field for a wire. Notice that it is proportional to current. So whatever the B field coming off the primary is will be proportional to that current. And this M embodies something about the geometry of this guy here. In fact, it actually embodies something about the geometry of the whole situation. Dang it. By Faraday's law, because I've got an AC circuit here, I've got an AC power source, my B field is going to be changing a lot. So that means that my electromotive force in the secondary is equal to minus N of the secondary. Changes in the magnetic flux in the secondary divided by my change in time. But these guys are equal to each other, which may not be the most obvious thing in the world. So that means I can force this into here. Basically, all the geometry of the fact, whatever's the distance between these guys and the shape and whatnot, it forced into this M, which makes them equal to each other for some definition of equal, which is it's a calculus pain in the butt to figure out M as the memory serves. And so this turns into minus change of M I primary over change in time. And so M is constant because it's all based off of geometry, so that's minus M change in current in the primary over change in time is the electromotive force in the secondary. Oh, okay. Well, so nobody said that the inductor couldn't induct off of itself. It produces a magnetic field, much like this guy does, and there's a magnetic field in itself. And so, because there's a changing magnetic field in itself, that means that this L can actually mean that the secondary coil is in fact also the primary. And so, this M here, this is mutual inductance. Inductance is M. But we also have L, which is self-inductance. So there's going to be an EMF in this circuit based off the fact of the inductor being present. So that's minus L, change in current over change in time. Okay. So, for the time being, there are two reasons to put an inductor into a circuit. One, this minus sign here is telling the circuit that it cannot change its current. So, one way to think about what an inductor does is that it stores current. Another way to put that is that it tries to keep current constant. So, not having brought my not having brought my laptop here. So, if you look at your own laptop, you have a power brick, and then a tab comes out, and then there's a cylinder. Back it off just a little bit. Got a cylinder, and then carries on, and then it's got plug into laptop. Got a power brick here. So what's this guy doing? So the power brick, what the power brick does is it takes incoming into it is 100 and back that up. Try again. Coming in is 120 volt AC. Coming out the other side is 12 volt DC. So, what it's trying to do, with what this power brick is trying to do is it's trying to provide a constant voltage, and if everything was going well, that would imply, if the workload of the laptop was constant, that would imply that the current was also constant, that the current draw would be constant. That's not entirely true. What happens is that the workload will vary, but it won't vary rapidly. So It'll vary a little bit this way and a little bit that way. But the brick will always provide 12 volts at whatever current is provided. So because to good approximation, the workload of the laptop is constant, that implies that the current is also constant. And so what this guy here is, he's called a choke. Why they do that, I don't know. Because it's actually an inductor. It's this curly brace here. This is curly Q. And this curly Q is telling the current that it shall be constant. And it's cleaning up any leftover indiscretions from this power brick going into the laptop, so that the current coming into the current and the voltage coming into the laptop are constant, and the laptop is happy. If it's not there, then it is possible that the voltage and current coming out of here won't be constant enough, and the laptop will be unhappy, and then it will shut down, and then you will be unhappy, and you will want to return the laptop for money, and the company does not want that. So they clean up the power coming into the laptop to make sure that the laptop stays happy and you stay happy. I was told in passing by a doubly once upon a time, a electrical engineer, that they would prank doors, that they would put a tiny so they got a door like so, and what they would do is they would put a small current, I through here, like as in microamp size. I goes in, and then it would come into the top of the door, through the latch of the door, into the door jamb, where it would then through the latch. So I comes in into here, through the latch of the door, and then back up the door jamb, back up to the source. So we got something like that. And in the process, they would include in here an inductor, where L was in the size of was something on the order of like 10 henries or something like that. And so and the reason they had let me show you I should have, where's there it is. So I built this inductor here for purposes which I intend to show you next week and a half, something like that. And so this guy is probably in the range of millihenries, which means that an inductor of the size of henries is ridiculous. And the only reason they had something that was that big was because at the time they were using fairly low frequency current and voltages. So they had reason to have a very large inductor hanging around their WE labs. Well, someone comes along and opens the door, opening the circuit. Now the circuit wants to go, instead of going through the door latch, goes through the person. But this massive inductor is saying the current shall remain. And so the person who has opened this door becomes part of the circuit and is now receiving milliamps of current. And it hurts, like the dickens. And they thought this was funny. Because, as I noted, one of the purposes of an inductor is to store current. So that's one of the things that inductors like to do. They want to maintain current. The other purpose of an inductor is to store energy. And so the energy stored in an inductor, E is equal to 1/2 Li squared. Huh. Okay. So the the energy density of the magnetic field, after working some stuff out, the book has kindly derived for us that the energy density of the magnetic field is B squared over 2 mu naught. And the energy density of a capacitor was something like epsilon naught E squared over 2. And so you add these guys together, you can see you end up with B squared plus an E squared. And so these two together, you can have some, if you played with your units right, you can find that the energy in the electromagnetic field is B squared plus E squared to within proper units. We won't do that. We'll just add them together. We probably won't do that either. But I just want to point that out. Right. I did mention that the unit of inductance is a Henry. So let's check that. Let's put that into context with what other units are. So we have that volts here. Minus is a number, don't care about that. We got the units of inductor, which is a Henry. And then we have here the current per unit time. So that's an amp per second. And so we solve for a Henry. And so one possible set of useful units for the Henry is a volt second per amp. There's probably a number of other ways to write that out with volts and amps and whatnot. So if you want to, you could say invoke Ohm's law, and then you get an ohm second, right? Because V is equal to ohm amp, right? V equal IR, yeah. So that's an amp ohm. So then you end up with amps over amps, and you end up with an ohm second. Or you can look at this amp here and you go, right, that's also a volt second squared per coulomb. So there's a number of ways to figure out what the units of Henrys are. I believe these are all equivalent. I don't know if any of them are more useful than next. So at some point it's like, what? Why memorize all these and just throw up your hands and give up on them? Anyways, as you can see from this guy here, you have the I and the T. So you got an amp per second here and a V over here. So that also means that the units of mutual inductance are also in Henrys. Questions about inductance? Hearing none. Hearing none, I'm going to store this guy. This guy we care about much more than this guy down here. This guy we care about. One moment. Get rid of this one. Nope. Try again. Alright, fine. Be like that. Oh, come on. I'll get all of you eventually. And this guy we care about. XV. Uh-oh. I'll just leave him in it. Oh, no, we'll move him somewhere useful. Put him there. XV. We'll put him here. And then we'll get rid of everything else. We don't need anything. I don't believe we'll need anything else. Store these guys over here. Nope, don't do that. I said store it. Thank you. We don't need that. Dot there. Okay. So, I have selected for myself problem number 50. GBUs at this time. Time. Oh, okay. I'm doing splendidly. I like this. Okay. Problem 50. Oh, I went to the next chapter. That's bad. Come on. Oh, okay. All right. Number 50. All right. We have the current through a 3.2 millihenry inductor. Okay, so that means I have some. We're going to provide some current here as a function of time. And I have an inductor that is 3.2 millihenries. And this F as a function of time goes like I in currents up to here is 4. Oh, not in seconds, but milliseconds. So here, here, and here. So this is 2, 5, and 9 milliseconds. Goes up to here, goes forward there, and then it drops down to there. Let me replace that unit one more time. This is in milliseconds. There we go. And that's up to 4 amps. Alright. So, the problem would like to know, what is the EMF from 0 to 2 milliseconds, 2 to 5 milliseconds, and 5 to 9 milliseconds. Okay. So we have an we're looking for the EMF, which is minus L change of I over change in time. We are told that this is minus 3.2 millihenries. The current, we'll go for A, the first one, is 4 amps. We're going to increase the current by 4 amps in 2 milliseconds. This milli cancels with that milli. And the answer is 3.2 times 4 divided by 2. Come on. Execute. Thank you. That'll be 6.4. 6.4. We got my sign here, so we got minus 6.4 volts. And then B, the EMF, is equal to minus 3.2 millihenry. The change in current between 2 and 5, well, it's constant at 4 amps, so that's 0 amps. Divide by 3 milliseconds. In this particular case, it doesn't matter because 0 times anything is 0, therefore the answer is 0 volts. And C, EMF is minus 3.2 millihenry. 9, nope. We're going to decrease by 4 amps. And the change in time is 4 milliseconds. Millis cancel millis. 4 over 4 is 1. And so this works out to be minus times minus is plus, so this will be 3.2 volts. Questions? Makes sense? Hearing no questions. Okay. So, if you need to write this down, I'll be posting it to my YouTube. Probably unedited. Sorry about all the coughing and hacking that recording. So, this guy here. So, remember how we had the this guy here. There's no reason why the secondary of the transformer has to be secondary and the primary has to be the primary. We could wire it in backwards. In fact, let me draw up a little diagram here real quick, like. So we got an AC thingy on here. It goes here. And then it comes down here. Inductor on that side. And then we put 2 bars down this center here. And then we have a load over here. Try that load again. Comes over here, up here. And then we have another inductor. Let's try the inductor the other direction. Up, over, down, inductor on that side. And ta-da. This is what is drawn into diagrams as a transformer. So, there's no reason, like so, but there's no reason why this side has to be the primary and this side has to be the secondary. I could turn this transformer around the other way. I could wire it the other direction for kicks and giggles and squiggles and all that. And so it's just as easy to say that the electromotive force in the primary is equal to minus the mutual inductance delta IS in the secondary over change in time. Because M is built off of geometry, M will be the same regardless of whether the P is here or the S is there. So these two M's will be the same. But that's right. Right. So, yeah, I've kind of written things down that's not entirely helpful. These are true, but they're not what I need to explain what's going to happen next. So electromotive force in the secondary is equal to minus number of coils, number of loops in the secondary, times the change of magnetic flux in the it doesn't matter. Apparently these guys are the same. And electromotive force in the primary is equal to minus in P change of flux in the probably in primary, or change in time. The M here is probably going to take into the consideration that any flux going on here, so they'll turn out that these are the same, apparently. And so you can set this guy equal to that guy, and so we can rearrange this. It turns out that the electromotive force in the secondary over electromotive force in the primary is equal to the number of loops in the secondary divided by the number of loops in the primary. Okay. Well, another thought here is that power is equal to I times voltage, which is the same as electromotive force is a voltage, so that can go right there, just like so. And since the power delivered to this side of the coil has to be equal to the power delivered to this side of the coil, that means that we can solve for I and make solve for the electromotive force, and so we end up with that P over I secondary is equal over P over I primary. Well, the power is the same on both sides, so these guys go away, and we turn everything upside down, and so it turns out that this is equal to I primary over I secondary. Okay. So the point of the transformer is to exchange by energy conservation. The point is to exchange current for voltage. So why in the Sam Hill would we do that? I got 3 minutes here, so I don't think I'll get quite far along. So the point of doing that is that power is equal to V squared on R. And so if we increase the voltage, we can decrease the current, which will decrease the magnetic field around our transmission wires, which will decrease the coupling to earth. And we can send more power with less current through our transmission lines, which is great and all until you get to wherever you're going, and now you need to put it into a house where your voltage needs to be in the neighborhood of 120 volts. And so you need to put it through a step-down transformer and bring it back down to reasonable levels. So that's the point of the transformer, and that is what made Tesla correct. So back in the day, Tesla and Edison had an argument about whether AC or DC was better. And so the thing is that in order to centralize your power production, get economies of scale, you needed to transmit your power over power lines, over transmission wires. In order to do that well, you had to step your voltage way up. In order to have it back in that day, in order to change your voltage, to exchange your voltage and current, you needed a transformer. And transformers only work if your current is changing and your magnetic fields are changing. And so that's why AC works. If you have a DC circuit, it doesn't work. Well, time progresses, and now Edison is right, because everything, our computers, run on DC, and now we have to convert our AC back to DC for our computers. And so now Edison's right, because everything else, all the mechanical devices, could run off of either. And so these days, Edison is right, and there are now DC power transmission lines that work off of solid state electronics. So, in my opinion, Edison is right, but he had to wait. And because we couldn't wait, Tesla won out. Anyhow, time has expired. I will see you alls on Thursday, either here in the Google Meet or in class. One of the two. We'll find out on Thursday. See y'alls in due course.